So there's another story that I didn't tell Greg, but at the same family reunion I met grand aunt, Pia, and I was trying to explain her also about my work, and so I spent some time describing the technical book we had just finished writing. And so she seemed to really understand and enjoy what I was telling her. But then at some point she turned to my grand uncle and she summarized what I was doing with the following words. She said, Gianfranco has just finished writing a book, a 700 pages book on something that maybe does not exist. Okay? So that was the summary of it. Anyway, so I'll do my best tonight to convince you that dark matter exists, and it's a real problem for astrophysics and cosmology. I will not. So, as I told to some of you during the reception, I will try not to spend like 15-20 minutes telling you the history of dark matter. Dark matter is like a pillar of modern cosmology, and what I want to do today is to try and convey the excitement and the interest and the enthusiasm of doing research in this field right now. So we'll do, just to introduce the subject, I will just tell you very briefly about the first hint of the existence of dark matter and dark planets in the sky. And then I will fast forward to what we know today about these particles, about this obscure component of the universe. So let's start from, the picture of a night sky. Some of you will recognize, I'm sure, Joshua Tree. So what you can see here is, probably some of you are familiar with the night sky, with constellations. This is the Orion constellation. And so if you move from the belt of Orion left, about 5 times the size of the belt of Orion, you see the brightest star in the sky, which is Sirius. Okay, so in 1844, Friedrich Bessel, and the engineers and physicists in the room would recognize this name. He was a famous astronomer and mathematician. He realized he was studying the position of Sirius in the sky, and he realized that the position was slightly. Seemed to be slightly perturbed. And it was not just a smooth movement, it just seemed to be perturbed by something else. So this is the guy, this is Friedrich Bessel, and in 1844 he published a paper where he suggested that Sirius was not just a single star, but a double star. Okay, so there was another star in the system, and the 2 stars were going around each other. So the small star, which was invisible at that time, was perturbing the orbit of Sirius. Okay, so this is how he phrased this hypothesis. And a few years later, actually I think over 15 years later, a very faint companion of Sirius, which was dubbed Sirius B, was discovered. Okay, now we know that this star is a white dwarf, as a matter of fact, a very small and faint object. But the way he did that, he was by studying the motion of an object in the sky and, just relying on the laws of gravitation, on the law of gravitation, Newton's gravitation, and predicting the existence of another star in the system. And he understood back then that the phenomena of varying motions, so these anomalies in the motion of stars and other celestial objects, seem also to possess interest in relation to our knowledge of the physical constitution of the universe. So he understood, almost 2 centuries ago, that just using gravity and just observing the motion of objects in the sky, one could say something about the stuff that you cannot see with your telescopes. Okay? So it was a very important moment in the history of astronomy. As I said, I will now fast forward to today, and I will summarize the status of and the evidence for dark matter with the following argument. So there are a number of observations in astrophysics and in cosmology that range from the observation of rotation curves of galaxies. That means you observe a galaxy like the Andromeda galaxy in the sky, and you look you measure how fast the stars and the gas move around that galaxy. You can perform also other types of observations. You can measure clusters of galaxies, so big conglomerates of galaxies in the sky. And you can go all the way up to the cosmic microwave background, which is the most distant probe we have of the universe. And you can even combine this with all sort of other probes we have of the distant, deep cosmos. And the picture that emerges is the following. Of all the matter in the universe, only 15% is visible, is formed of normal matter. And in fact, out of this 15%, only 1% is made of stars. So imagine when you put your eye, when you look through a telescope, and you see galaxies and clusters of galaxies and so on. So most of it actually belongs to this top 1% of this matter iceberg of the universe. 7% is in the form of gas in structures like galaxies and clusters of galaxies. And another 7%, we are quite confident we know where this gas is, and we measure it quite well. There's another 7% which is much more hard to measure because it is in this form of this diffuse gas in between galaxies. Okay? But so all the matter we know, all the atoms, all the nuclei that we know amount to 15% of the universe. The bottom 85% is also some form of matter in the universe, but we have no idea of what it is. Okay? So in this particular talk, what I want to do is to tell you what are our ideas about what this component of matter in the universe is, and how we can prove that the theories we are proposing are correct, or how to rule them out. So in this plot, I'm not showing you the other elephant in the room, which is dark energy, which is another embarrassment for cosmology. And the reason why I don't talk about it is that it is, as far as we understand, it is probably something very different from dark matter, and we are even more far from understanding what it is anytime soon. So I want to go step by step and tell you a little bit about dark matter. So if you believe, what I want to really, this to be clear, this is not like an exotic model. I'm not proposing anything weird or bizarre here. This is standard cosmology. If you open a textbook of cosmology, this is what we think the universe looks like. So in particular, if you think about a galaxy, some of you have seen pictures like this. This is the Andromeda galaxy, which is a galaxy, our sister galaxy. We probably, the Milky Way we live in looks actually very similar to Andromeda. For many years, basically from when people realized that there were these objects in the sky, there were separate galaxies, so we're talking about 1920s or so. Up to the 1970s, this was the picture that an astronomer had in mind when he thought about a galaxy. Today, you are forced, from actual observations, you're forced to think of galaxies as something like that. Okay? A small disk of gas and stars sitting at the center of a much, much larger distribution of matter, which is unknown. Okay? We know it must be fundamentally different from anything we know. How do we know that it must be fundamentally different? Here is a list of 10 properties of the dark matter. I will not go through all of them because it would be a bit boring, but if you have specific questions about it, I'll be happy to answer them. But this is formulated, this was an exercise, if you want, to tell particle physicists, so people writing up theories of fundamental interactions, what properties the new particles they were postulating had to fulfill in order to be considered viable dark matter candidate. So the reasoning here is you have a particle physicist. He's trying to extend the standard model of particle physics. He proposes new particles. And we give the particle physicist this test. And his or her particles have to fulfill all these properties to be considered viable dark matter candidates. And this more or less reflects what we know about the particles, the dark matter particle. So let me go very quickly through it. First, for every particle that is proposed, so for every extension of the standard model of particle physics, you have to make sure that the particles that you propose possess the appropriate, what is called relic density. So basically, these particles must exist in the universe with the appropriate abundance. Okay? They must explain the dark matter on all scales. You want these particles to be cold, and if you're interested, I can tell you specifically what this means. They must be neutral, so nothing that is charged, like an electron, a proton, nothing like that can act as the dark matter. It must be compatible with the calculations we make of the early universe. It must be compatible with everything we know about the structure and evolution of stars. It's actually very easy to propose new particles, but when you try to study the consequences of postulating these new particles, it's very easy to destroy stars completely. And you don't want that, right? You know that stars exist, so anything that does that is not the correct answer to the dark matter problem. And then in the bottom row, points 6 to 9 are constraints on the interaction of dark matter particles among themselves and with ordinary matter. Okay? And I will come back to this point in the rest of the talk. Right now, what I want to show you is that there is a 10th point that is more like a philosophical point rather than a physics point. We insist that it must be possible to test these particles somehow. It is perfectly possible that nature has not been kind with us, and that these particles only have very, very weak interactions with any of the particles we are familiar with. So it is possible, for instance, that these particles only interact through gravitation with the particles of the standard model. And if gravity is all they do, then the only observation we can perform is the one that we have already performed, which is that they have gravitational consequences on the motion of objects. So if they have no interaction whatsoever with us, this would be a very unfortunate case for physicists trying to understand what these particles are, but it is still a possibility that we have to keep in mind. Okay, so if you just run through these properties, you basically exclude all the particles of the standard model. Just think a particle of the standard model, the electron is charged. It cannot be the dark matter. The proton is charged. There's strong interactions. It cannot be the dark matter. You can go through all the particles, including neutrinos, which for many years were thought to be good dark matter candidates, neutrinos that belong to the standard model of particle physics, and you can rule them out. Okay? So there's no known particle that can act like the dark matter in the universe. Okay? So this is the strongest evidence that we have today that there must be new physics, that new particles exist. Okay? All right, so you may ask, so what are these particles? You've shown us some properties of the dark matter particle. Are there new particles that would fulfill all these properties? And if you talk to people in this field, they will mention one name. And I encourage you to keep this in mind because this is the most promising candidate that we have for dark matter. The name for this particle is the neutralino, and it arises in the framework of theories called supersymmetry. I will go back to this point. So many people now, even when they think about dark matter, they just identify in their minds dark matter equal neutralino. But you have to keep in mind that particle physicists are very creative individuals. Okay, so this is a partial list of candidates that have been proposed in the literature to explain the dark matter problem. Okay, so it's not that we don't have enough ideas. It's just that it's very difficult to prove or rule out these ideas. And today I will argue actually that we might be, we are very close to proving or disproving at least one big category of particles. So in a way, so when you open a particle physics journal, sometimes it feels like reading one of those Middle Ages bestiaries, where there are all these, strange creatures mingling with, normal beings. So somehow what particle physicists are doing is basically to fill the gaps in their geographic maps. So this is the Psalter map that was drawn in 1260, and this is the British Library in London. And this is a map of the known world back then. And it is arranged in a different way. It would take some time to explain, all the amazing content of this map. But the interesting thing is that at the bottom here, there's Africa, actually. It was largely unexplored by people living in Europe. And what they did here, these geographers, they put all these, bizarre creatures, these monsters, they were thought to live there. So in some cases, they are like mythological creatures. In some cases, they are just, distorted perceptions of real human beings, very tall, very short, very, anything. And in fact, Jonathan Swift was bitterly mocking these geographers. So geographers in African maps with savage pictures fill their gaps, and over inhabitable downs place elephants for one of towns. So maybe we are doing something similar here. We are imagining some monster that would explain things we don't understand. But we hope that just some of these creatures turned out to be just distorted perception of, actual real animals and real people. We hope that at least one of our candidates turns out to be the dark matter in the universe. So just to arrange in a logical way all the particles that I've shown you, let me just divide them in two broad categories. The first category is that of WIMPs, an acronym a bit pathetic, I admit, but that stands for weakly interacting massive particles. Okay, and then there's everything else. Okay, so it is a bit unfair. You may think to divide the candidates to arrange the candidates this way, but actually there are very good reasons to believe that the dark matter particles should have interactions at the weak scale. So when I say weakly interacting, it just doesn't mean that it doesn't mean only that these particles have very weak, in the common sense, interactions with dark matter, but also in the particle physics meaning of the term. So weak interactions denote a very particular type of interactions in the standard model of particle physics. And we believe, many of us believe that dark matter could really have something to do with the weak scaling particle physics. And there are very strong motivations. And I'm happy to tell you more about that. So for this particular talk, I will ignore, since I want to show you some results, not just, describing, monsters. I want to focus on this category of WIMPs, and I want to argue, actually, that we might be very close to finding these particles with the new generation of particle physics experiments, or to rule out their existence. Okay, so this is my goal today. The way we do this is through three different types of experiments. One is, I'm sure, familiar for many of you, which is the category of collider searches. So I'm sure you've heard about the accelerator, the particle accelerator in Geneva at CERN, the Large Hadron Collider. So this is what we are talking about. And the other searches are direct detection. So these are experiments that are placed deep underground. And indirect detection that usually exploits data from telescopes that are placed in orbit around the Earth. Okay, so we have on the surface, or just a little bit below the surface, very deep underground, and in orbit around the Earth. So in the subtitle of this presentation, I told you that there is a worldwide race for the discovery of dark matter, and I'm noticing that you aren't asking questions. So if what I say is not clear, please feel free to say so. So I mentioned this worldwide race, and this is actually what is going on right now, basically, literally worldwide. So this is a list of experiments that are searching for dark matter. Let's start from the yellow points. So the Tevatron, actually, at Fermilab was recently shut down, and its successor, the Large Hadron Collider at Geneva, has already taken data for a few years, and it will restart again in end of 2014, end of next year, start of 2015. Then there are dedicated dark matter experiments. So these experiments, where there are these red dots here, you have all these underground experiments, placed below 2 kilometers of rock, basically. So very deep underground in mines and underground laboratories. And they perform dedicated searches for dark matter. So these experiments are just built to search for dark matter. And you see there are many of them. All these names refer to experiments, direct detection experiments of dark matter. Then there are a number of other experiments which I will not discuss in this talk. There are gamma ray telescopes. Actually we'll mention at least one, this HESS telescope in Namibia. There are neutrino telescopes. One of them is producing fantastic data at the geographical South Pole, in the ice, so below the surface. And there are a number of neutrino experiments also in the Mediterranean. Okay, so and let me just mention that there are also 3 satellites that are providing incredibly interesting results. One is the NASA satellite Fermi, a gamma ray telescope. Another one is an Italian and Russian telescope called Pamela. And the third one is attached to the International Space Station in orbit, and it's called AMS-2. Okay, so what I will do now is we have 25 minutes. I will try to spend, say, like 8 minutes on each of these detection strategy. I would like to tell you a little bit how the principle, what is the principle of detection, and I want to tell you at least one interesting thing for each of them, one recent result for each of these detection strategies. So let me start from indirect detection, which is actually the one that you can perform with satellites and with air Cherenkov telescopes like the one in Namibia. The key idea here is the following. I told you that there are these particles that are called WIMPs, weakly interacting massive particles. Now, the reason why they are interesting is that these particles can annihilate, so they can just collide with each other and produce ordinary matter. Okay? So you collide 2 dark matter particles and produce electrons, protons, quarks, particles of the standard model. In the early universe, this annihilation process is in equilibrium.
Is that conjecture, or is that dark matter?
So if you make the hypothesis that they are WIMPs, that's true. That happens. You can calculate what is the annihilation cross-section for that particular. So for instance, if you assume that the dark matter is the supersymmetric neutralino, you can calculate what is the rate for these interactions. And what you want to do is to make an assumption that dark matter is a neutralino, calculate what is the flux of gamma rays or other things, and then compare this with observations to see whether your conjecture, your assumption, is correct. Okay, so you go full way in the scientific method. Okay, so you start from dark matter, you annihilate into particles of the ordinary matter, and the interesting thing is that these particles are in equilibrium in the early universe. So there are as many particles of dark matter annihilating to particles to ordinary matter particles than ordinary matter particles annihilating to dark matter. So this reaction goes in both directions, actually. Now, what happens is that if the strength of the interaction, so the probability that these 2 particles collide with each other, is at the weak scale. So if the strength of the interaction is weak, then you can produce dark matter with the correct abundance in the early universe. So at some point, the universe expands. As the universe expands, these particles will not manage to find each other anymore unless their interaction strength is very large. And at some point, these reactions basically doesn't happen anymore. And the number of particles of dark matter in the universe basically remains frozen. And that the universe expands, this remains a constant, basically, which is what we measure with our experiments. So we think we can calculate what is the probability that two dark matter particles, if we assume they're WIMPs, annihilate. And what you want to do is, as we were saying, to calculate how many particles annihilate, so collide with each other, for instance, at the center of the galaxy we live in. Okay, so we live in the Milky Way. We live 8 kiloparsecs, which is, few tens of thousands of light years from the center of the galaxy. We can calculate how many annihilations of dark matter we have there and how many particles are produced at the center of the galaxy. And then we can compare with observations. We can make a prediction. We can say to our friends doing observations, we expect to see a flux of high energy photons, very energetic light from the center of the galaxy. Or we expect to see so many electrons or positrons or antiprotons and so on. In order to do this, we need to estimate how much dark matter there is at the center of the galaxy. And this is done usually through numerical simulations. So what I'm showing you now is how people believe that structures like the Milky Way, like the galaxy we live in, form in the universe. So this is a movie that starts from a very early time in the universe, and you will see that a big structure of the size of the galaxy we live in will form at the center through the merger of smaller objects. Okay? And this is a dark matter only simulation. This is how it goes. So I have a rather homogeneous distribution of dark matter at the beginning, and then the small halos of dark matter merge into bigger systems. And every time they merge, so follow for instance this clump here. It merges with the big halo and it sheds a lot of matter in the host halo. Okay? So at the end of this formation process, when this quantity goes to zero, that means redshift equals zero, means today, you form halos which have the size and the mass of the Milky Way. Yes. It's only dark matter here. I will add matter in the next movie. Okay? So from a gravitational point of view, dark matter dominates the formation of big structures. Okay? So you have to follow how dark matter halos merge into bigger, larger and larger systems. Okay? So what this movie shows is you start from, this is with matter. So it shows you start from many small halos of dark matter, and you follow, as time goes by, these halos merge and create bigger and bigger halos.
Are those like stars of dark matter?
No, they're not. They're very diffuse, actually. It's very difficult to confine dark matter in a small space. This is what characterizes, actually, dark matter. And there is a very good reason for that, actually. In order because you may wonder, for instance, why dark matter remains distributed on large scales where galaxies form disks right at the center. And the way this happens, I can show you the next movie where I actually include baryons. This is done by a group, Oscar Agers, who was previously at Zurich and now is in Chicago. So this is another movie that shows the evolution of the gas density, the temperature, and the chemical composition, something else. But just focus on the blue, for instance, the blue contours. You see that there are blobs of gas merging at the center of this structure. And what happens is that whereas dark matter basically only interacts gravitationally, all the stars and the gas, they radiate away energy. Okay, so they just lose energy. And through this loss of energy, they can be confined in smaller and smaller systems. Okay? Anyway, yeah. It is. So in those simulations, you just assume certain initial conditions and then just let the system evolve through standard gravity. Okay? It actually, if you just run simulations like that, just assuming only gravitational interactions, this reproduces the distribution of matter on large scales very, very well, actually.
What represents the bouncing off of some of these dark matter entities from other dark matter entities? If it was just pure gravitational, why would they bounce off?
No, they don't bounce off. Actually, what happens is a process called the tidal stripping. So you have a system where a bound system falling in a much larger bound system. Okay, so as you fall in, the particles which are in the outer parts of the system that is entering in the bigger system, they feel the gravitational pull of the big system. And they exert what are called the tidal torques, which are the same type of forces that produce tides, right? So some of these, of the matter of the outer shells of this system, which is merging with the bigger system, will be stripped from the small system, and it will go to produce this diffuse halo of matter in the big system, okay? So once you quantify how much, through these simulations, how much matter there is at the center of the galaxy, you can calculate how many photons, for instance, you produce at the center of the galaxy. And then you can, again, go to your favorite experimentalist and say, could you please point your telescope to the center of the galaxy and see whether you see any signal of this type. And this is what people have done, for instance. They've compared their predictions with the data of this experiment, which is the Fermi satellite, that has produced this type of maps. So this is a full sky map of the sky in gamma rays. Okay, these are actual data. If you, with your eyes, you could see gamma rays. Looking at the sky, you would see something like that. What you see, so this is in galactic coordinates. So what you see here, this plane is the plane of the galaxy. And the most interesting region for dark matter searches is right at the center, where, which corresponds to the center of the galaxy. Now, the most interesting result, I promised I wanted to show you, recent results. The most interesting result, which was, really debated for many days, actually, during the dark matter program we are running here at the KITP, is the observation of a line. So photons at a very particular energy, which is 100, in units of GeV, they are usually given. So in this particular unit of energy, you see that there is a line at this particular energy. So in practice, what you do is the following. You collect data, you collect photons from the center of the galaxy, and you plot what is the energy of the photons you get. And what you see is that at 130 GeV, here, there is a little bump. So by eye, probably doesn't tell you much. It's not very prominent. But if you perform a statistical analysis of this, you have the detection of a line of photons towards the galactic center. Okay, so this is a subset of the bigger map, which is centered around the galactic center, and this is the region where you observe these photons. Okay, so this article was published in 2012, actually. And since then, many physicists and astroparticle physicists have tried to check whether there is actually a line that would point directly to an explanation of dark matter. There is basically no way, using standard physics, to produce a line at the galactic center. But there is, an obvious way in which you could produce a line with the annihilation of dark matter directly to photons. So this might be a hint of dark matter. If we accumulate more data, and this line becomes more prominent as we accumulate more data, then this is one of the most interesting results of the last few years. Now the question is, and this is what we have discussed here in this program, what is the origin of the line? For instance, is it possible that, for some reason your instrument is such that, for some reason it produces lines at this particular energy? So is it possible there is some systematic effect, some instrumental effect that produces lines of this type? And there is a consensus that probably in order to cross-check this observation, we need to use a different telescope to observe this line signal. And fortunately, this HES-2 telescope was recently added to the previous array of telescopes in Namibia. So they look for gamma rays, and they can be pointed towards the galactic center. As you see, the scale of these telescopes is quite large. They are about, I think, 18 meters in diameter. This particular has two. It was the first light for this telescope was in 2012, and we recently spoke with the spokesperson of the collaboration. They told us that the galactic center is very high on their priority list, so they are commissioning right now the instrument. We hope to have results and to confirm or rule out the line within the next few months, basically. Okay, so let me move on to direct detection. And if you have any question on indirect detection, I'm happy to go back and clarify doubts you may have. The principle of direct detection is completely different, and it's actually straightforward. So what you want to do is you build an experiment, and you wait for a dark matter particle to enter your experiment and collide with one of the nuclei in your experiment. Okay? What you want to measure is the energy that is given by the dark matter particle to the nucleus in your experiment. This is the measure you perform, which is what is called a recoil energy of a nucleus struck by a dark matter particle. And people working in this field have devised many ways of measuring this energy. But you can imagine how difficult it is. Even if conceptually it's so easy to make even a calculation of how frequently these particles interact with the nuclei in your detector. You have all sort of particles entering your detector and hitting nuclei. You have cosmic rays entering the atmosphere, producing particles that hit your detector, and so on. Radioactive elements producing particles and hitting the detector. So in order to perform this measurement, what you need to do is to shield the experiment from any cosmic radiation penetrating from the upper atmosphere. So what you do is you take your experiment and you bring it underground as deep as you can. And some of these experiments are basically buried below 2 kilometers of rock. Okay, so very deep underground. The way this works in practice, I just want to show you what a real experiment looks like. So the most sensitive experiment on the planet is Xenon 100. That's the name of it. And it's big like this. Okay? So it's not a huge machine like the LHC that we will discuss in a moment. It's big like this. And its successor is a Xenon 1 ton, which is about like a meter tall or so. The way this works is you put liquid xenon, so this noble gas, in your detector, and as a dark matter particle enters in your detector, you produce different types of signals. You produce like ionization signal, and you collect the light from it, and some electrons that produce further light. So if you're interested in the details, happy to tell you more. But the bottom line is that you have ways in these experiments to measure the energy deposited by dark matter particles in these experiments. Okay? So just to scare you a little bit, I wanted to show you how we actually calculate these things. In fact, this was not to scare you, but just to tell you that these things are not just guesses. We can actually calculate, for each model of particle physics, we can actually calculate what is the interaction rate in an experiment like Xenon 100. We can make very accurate comparisons between predictions and observations. And when we do these calculations, there are many parameters that enter. So we need to specify what is the particle physics, what is the astrophysics of it, and so on. But just to summarize what the status of the field is, let me show you this slide. It is the only slide I will show you about direct detection, but hopefully this summarizes what the current status of searches is. Okay, so this is a very busy slide. Let me walk you through it. We have on the x-axis we have the mass of the dark matter particle. A mass of 1 GeV would be the mass of 1 proton, and then it's 10 times, 100 times, and 1,000 times the mass of the proton. Okay? On the y-axis, you have the strength of the dark matter interactions with ordinary matter. So the larger the strength of interaction, the larger the number of events you would expect to see in these detectors. So far, we have not seen in a convincing way events, dark matter events in direct detection detectors. So the best we can do is to draw lines in this plot and to say, so for instance, this is the line drawn by the CDMS2 experiment in 2010. This is the line, which is the current status of the field, drawn by the Xenon 100 experiment last year. And these lines tell you that the interaction of dark matter cannot be stronger than what indicated by this line. Okay, so this is the best we can do so far. There is no dark matter event in our experiments, so we can only say that the interaction cannot be larger than a certain amount. A number of experiments, and the last one was discussed a lot in this workshop we had here at KITP, was the CDMS2 experiment, right down here. And if you're interested in understanding what these blobs represent, just feel free to ask questions.
I actually have 3 questions.
Wow, okay.
Since the beginning, I've been wondering, you were talking about WIMPs, and I figured everybody else in this room already knew this, but I'm going to ask it anyway. Do you mean that it has to do with the weak force at all? Or is it just that they weakly interact?
They have to do with the weak force. That's the short answer, yeah.
Thank you. That answers the first question. Second question, why did they use xenon? What's special about xenon to help find these dark matter particles? And then third, why is it that the lighter the mass, the more strength of interaction? Somehow I would have thought if it was more massive, that, more interaction, less mass, less.
Right, okay. So why xenon? Because when you calculate the rate of interactions, the larger the nucleus, the bigger the signal. Okay, so you can show, through that formula that I was showing you, working out the details, you can show that you want big nuclei to optimize the chances of detection. And xenon has, not only that particular property of having a big nucleus, but also it has very good signals for the ionization and scintillation, which are, the 2 quantities that you measure when you want to measure the energy deposited in the experiment. So from an experimental point of view, it is just, great, and this is why people use it. But it's not the only one that is being used. So for instance, people use germanium and silicon in CDMS too. Okay, so there are other things. I just finished to answer the third question, which was about the shape of this line. I would say this a bit quickly, but if it becomes unclear, maybe we can go back after the talk and discuss it more. So what happens here is that each experiment has basically a minimum energy it can detect. Okay, so below a certain energy, it cannot detect anything else. It's just an instrumental property. And so when the mass of the dark matter particle becomes very, very light, the energy they deposit in the experiment becomes very low. And your experiment basically loses any capability of constraining the parameter space. So this is why these lines go up very quickly. This is unclear, right?
Well, the parameter space is not whatever you just said. That makes the line go up.
The line goes up because your experiment is not sensitive enough. Okay, so you cannot exclude a cross section down here, because a particle that with this mass would deposit a very small amount of energy in your detector, and your experiment is not sensitive to that energy. Okay. No, actually, even if you work in a specific framework, like supersymmetry, for instance, the 2-parameter space, you can find, models that would produce a signal here, but not in indirect detection, and vice versa. So they're really complementary probes. Okay. Okay, so I'll try to wrap this up in 5 minutes, okay? Is that okay? Okay. Okay, so last type of searches. We've seen indirect detection, with satellites searching photons for the galactic center. We've seen direct detection, placing things underground and waiting for dark matter particles to interact with them. Let's look at the LHC. So the LHC is this 27 kilometers ring below the border between Switzerland and France. And inside, along this ring, you have experiments like ATLAS and CMS, which are really huge experiments. They are like 50 meters tall and 45 meters long. They're huge, huge experiments. And they are all instrumented and they search for new particles. Okay, so let me skip this. So this is, if I can get your attention on this particular slide, and then, I have only one more to show you. This slide shows you how people hope to extend particle physics in the future. Okay, so in the bottom part of this plot, all these red symbols show all the particles of the standard model we know, and we have measured them with a great precision. Okay, so these are the quarks inside atomic nuclei. These are the leptons, the electron that goes around the nucleus, the muon, the tau, the neutrinos, and the gauge bosons. Okay, so these are particles we know and we measure. We are sure about it. This is, textbook physics. The idea is, in theories like supersymmetry, is that there is, a new level of physics that we hope to have access to with these experiments as we increase the energy of our experiments. And in many of these theories, what happens is that to every particle of the standard model, there is an associated super partner in the language of supersymmetry. So there is a partner in this new theory. And you have partners for the quarks, partners for the leptons, and partners for the gauge bosons. It all becomes this is all very interesting from a particle physics point of view. Where this becomes interesting for cosmology and astrophysics is that the partners of these particles here, of these gauge bosons, have precisely the properties that are needed for a particle to be a perfect dark matter candidate. Okay, so the existence of this particle, I told you about the neutralino. This is what a neutralino is. Okay, so this is a partner of some of these particles of the standard model, some of these gauge bosons. Okay, and as a bonus out of your theory, you get a particle out of a theory that you propose for completely different reasons. To explain, the fundamental distinction between bosons and fermions, unification of forces, and so on. You get as a bonus the existence of a dark matter particle. And the way you search for these particles is like that. You collide protons at LHC. Okay, so you have beams of protons going around. You make these protons collide inside a detector, and we know how to do this, with a fantastic precision. And what you hope to do is to produce some of these particles here, for the partners of the quarks. If you manage to produce them, so if the energy of your experiment is sufficient to produce the particles of these particles up here, then you can follow what happens when they decay to lighter and lighter particles until they decay in this lightest particle of the theory, which is the neutralino. Okay? So as they collide, they produce all sorts of other particles. You collect all the particles that are produced, and you detect this particle here because it leaves your detector without leaving any trace in your detector, in any of the detectors. Okay? So it shows up as an imbalance of energy. You collide particles, you observe something, and when you try to reconstruct something, you see that there is something huge missing in some direction. Okay? So people have performed these searches, and this is a summary of these searches, which I will not discuss in detail. The bottom line is that the LHC has found no physics whatsoever so far. We found the Higgs, but the Higgs belongs to the standard model of particle physics. What we hope to do is to extend the searches for new physics in the future. There's a new run of the LHC starting at the end of next year, 2014, and then beginning of 2015. And we hope that we will be able to detect new particles with the LHC. And we hope that combining this information with the information that arises from direct detection and indirect detection, we can actually identify dark matter particles. I had 2 slides about the complementarity, but I stop. I mean, if you're interested, feel free to ask. I'll stop here because I'm running a little bit over time. So let me give you the conclusions, the take-home message. First of all, there's a huge theoretical and experimental effort towards the identification of dark matter. Thousands and thousands of people are working to try and detect dark matter. I've discussed indirect detection, direct detection, and the LHC. If there is one important thing to keep in mind, we probably need more than one of these searches in order to identify dark matter. And I really think that the next 5 to 10 years are really crucial to test the WIMP paradigm, so the existence of WIMPs. If we do not find the WIMPs, these weakly interacting massive particles, with the LHC, as it starts in 2015, and with the new generation, with the next generation of astroparticle experiments, we can probably, rule out quite robustly the entire paradigm. And I'm happy to discuss this further if you're interested. And as last message, I just wanted to thank the director and the KITP staff for hosting us. We've run a 10 weeks program on dark matter. We've had many new ideas, many collaborations that arose from this. So we are really grateful to you guys actually for supporting us. Thank you very much.
Okay, so I already see some hands. I'm going to come around with the microphone so you can ask your question and everyone can hear what it is. And if you have to leave, just get up and leave. That's fine.
Thanks. Can you go back to the slide that had the 10 criteria that we have to pass? And then I have 2 questions. One's going to be on that slide, and it's basically the current experiments that are, I think you just passed it, there you go, that are underway. Which of these criteria are they most focused on?
Yeah.
And then my second question is, are there any feasible theories that are not in the realm of particle physics, more mundane than new particles?
I didn't get the second question, sorry.
It's basically, so all of the candidates that you've talked about are in the realm of particle physics, new particles. Are there any explanations that are still viable that are not particle physics?
Yeah. Okay, so you can map directly different searches. This 0.7 is about couplings of dark matter with baryons. This specifically refers to direct detection. So these particles entering the detector and leaving some recoil energy you measure the recoil energy of the nuclei struck by dark matter particles. This is 0.7. And indirect detection is basically points 8 and 9. And so this is, in particular, the consistency with gamma rays is what I briefly discussed when I compared with the sensitivity with the map obtained by the Fermi satellite. And these other astrophysical bounds, they include things like the constraints that arise from, neutrino telescopes, or synchrotron emission, and things like that. So that's indirect detection, points 8 and 9. Oh, yeah, sorry, I forgot to answer that. Yes, and I'm actually pretty sure that if we fail to discover WIMPs, we might need to basically to rethink our approach to this data. So it is in particular possible that, so as I mentioned, all the evidence we have for dark matter is purely gravitational. So it is possible that it's not that you need new forms of matter, but maybe you need new forms of gravity. Okay, so in the past we've seen that the outer planets of the solar systems, like Neptune, were discovered through perturbations in their motion. So, for instance, Neptune was predicted by a theorist who was studying the motion of Uranus. and it was found precisely where Le Verrier had predicted it to be. Planets like Mercury also had some anomalies, but in order to, and Le Verrier actually proposed a new planet to explain that. But it wasn't until Einstein came up with a theory of general relativity that we could find an explanation for that, and the planet Vulcan was never found. So we have good reasons to believe that this type of approach is the most sound, because there are some observations that tell us that it's very difficult to modify gravity in a way that can reconcile all the type of observations we perform. But maybe there is some even more clever way we haven't thought of that deserves to be studied.
Question over here.
I'm still dealing with the indirect measurement where you found a peak at 130 GeV.
Yeah.
I assume that meant you had particles around 65. And
No, it's actually 130 because, sorry, you need to go through the list again. Because you have two particles colliding and producing two photons. So each of these photons carry half of the total energy, which is the sum of two particles, which is 130 plus 130.
But you showed a peak at 130.
Yeah, so this is the process that I'm referring to.
Each photon.
That's right. So you have two dark matter particles annihilating and producing two monoenergetic photons, each of them 130 GeV.
All right. Then you showed a slide later on showing a bunch of constraints.
Yeah.
I was wondering how this fit into those constraints.
The direct detection constraints. You mean this? This one? No? Which one?
The long list that you couldn't read.
Oh, yeah, that's particle physics. These are the constraints you get from accelerators.
Yeah. Did this survive that?
It did. Actually, if the line is produced, if there is a line, and if you interpret this as due to the annihilation of dark matter particle, it is probably not supersymmetry. So the leading theory, supersymmetry, probably has nothing to do with it, because it's very hard to produce, a single sharp line in that theory. So the particles in the neutralinos in that theory tend to produce, yes, a line, but also a lot of low energy photons, which are not observed with Fermi. Okay, so these constraints apply in particular to that theory, the theory of supersymmetry. If there is a line, these are probably irrelevant for that.
You started your lecture with saying that about 85% of all the matter is dark matter, and 15% is physical matter. So if I think about this from a perspective of cross sections or rate constants or something like that, how do you go from physical matter, which probably has a much, much smaller cross section given it's so small, otherwise you'd have much, much more physical matter than you would have dark energy if the cross section was higher from a perspective of collisions. How do you go and think that you're going to discover from that perspective the direction of dark matter as opposed to going the other direction?
I didn't get the question.
Okay.
Yeah.
So, pardon? Parthenogenesis. Yeah.
So let's see.
That's a good way of putting it.
I still need to understand a bit better. So you have normal matter. Yeah.
Perspective of 85% of the stuff is dark.
Yeah.
15% is confidence is obviously going to be dark.
Mm-hmm.
If in fact you had a larger cross section going from physical to dark, that would be reversed because most of it would actually end up becoming physical. So if you're doing experiments in the visible space, which implies to me that the probability of that actually occurring is much smaller than the other way around, how do you think you're going to be able to find it? Because obviously it's such a small process.
Right. So the way you attack this problem is, so first of all, it is not possible to do it in a model-independent way. Okay, so you cannot just say, have dark matter. Let's build an instrument to detect it. For the very simple reason that the mass of this dark matter particle is unknown over a scale of tens and tens of orders of magnitude. So it could be a milli electron volt. It could be 10 to the 16 giga electron volt. Okay, so the only way you can attack this problem is in the framework of a theoretical model. Now, the way you do this is suppose, for instance, that it is supersymmetry. Now, in supersymmetry, what I do is I take neutralinos as a dark matter candidate, and I calculate how many neutralinos I end up with in each portion of the parameter space. So just to give you an idea, supersymmetry has 120 free parameters. Okay, this is what we are talking about. And I can go to the parameter space and select portions of the parameter space where the proportion between normal matter and dark matter is more or less a factor of 5 or 6. Okay? If I change that ratio, I could still have an explanation in terms of supersymmetry. If by chance we had the proportion inverted, it could still be dark matter, the supersymmetric dark matter. Yeah, that's right. That's the type of problem we're facing. But that's right. That's right.
Excuse me for such an elementary question, but how do you calculate the mass in all of the stars, and what are the error bars?
The mass of a star, you typically
all of the stars. I mean, the 1% figure.
Right. Yeah. So it is tricky. So let's see. Typically, what we do is we measure the light coming from a galaxy. And we know, because we can calibrate these things on, local distribution of stars. We know what is the so-called mass to light ratio. So if we see, that many photons, that much light from a system, we know how to convert this into a stellar mass. Okay. Now, there are, of course, many other things. So, for instance, you have gas in the systems. And, depending on the specific system, there are different techniques. If you go on the scale of clusters of galaxies, the gas in the system glows in X-rays. And we know to associate the X-ray emission to the mass of the system under certain assumptions. We know also that these estimates are correct because we have other ways of measuring the mass in the systems through things like lensing, for instance. So we can build a sort of consistent picture of how much total mass, so dark mass plus gas plus stars, there is in a system like a cluster of galaxy. We can measure how much gas there is, and we can count how many galaxies there are. So we have different ways of measuring things, and we believe we have a pretty decent description of these systems.
Back when you were talking about the 10 requirements for the particle,
yes.
One of them was collisionless, and I don't know what that means.
Yes. Okay. Yeah. So actually, I can show you a bit more precisely what it means. So in a nutshell, what it means is that it does not scatter with itself. So it's very hard for these dark matter particles to collide with each other. Okay? Right, but these are two different processes. In one process, when I talk about annihilation, these two particles basically disappear, and they transform their mass into particles of the standard model. In this particular case, you're talking about scattering. So particles, the dark matter particles scattering, colliding with each other and not transforming into anything else, let's say. And there are constraints actually from systems like this, which is the, some of you are familiar with it, which is the bullet cluster. So what you see here is there are two clusters of galaxies, here and here. And actually the way you detect them is through lensing. So through this principle of gravitational lensing, you can find where the mass of these clusters is. And you find that the mass is concentrated here and here. And when you look where the baryons are, so where the gas is in the systems, you see that it is in these red blobs here. So when you try to interpret systems like this, you see that there are these two blobs of matter, which is mostly dark matter, have gone through each other without basically interacting at all. And from this type of observation, you can set a constraint on how strongly these dark matter particles collide with each other.
We have time for one more question, then I'll close it up. Well, I think I'll ask it. I'm an ignorant biophysicist, but let's take the supersymmetric model that you were talking about. The gauge bosons, their partners would be fermions. Fermions plus gravity. Why can't I have dark matter stars? That is, why couldn't I have a star completely composed of dark matter?
Okay, so there is one simple answer and one which is a bit more complicated. The simple one is if you take a distribution of dark matter which has more or less one solar mass. Its size is actually, I know the numbers for an object which is an Earth mass. Okay, the size of this object is the solar system. Mm-hmm. Okay. So in order to produce something more compact, you would have to find ways to produce to lose energy for these dark matter particles through some interactions, but we have strong constraints on these interactions. So this is the simple one. The most complicated one is that it is not easy to make a star completely out of dark matter, but it is possible to produce what is called, what some people call a dark star, in the sense that if there are baryons sitting at the center of a large distribution of dark matter, these baryon annihilations that we are searching for with indirect detection experiments, they inject energy. They inject photons and antiparticles and all sort of other stuff at the center of this object. And this object could basically act as a star, but instead of nuclear reactions at its center, the object would be supported by the energy injection of this dark matter particles annihilating with each other. Right now, this is more like science fiction than actual science, because we have basically no probes to detect these systems or to check.
But this sort of hybrid star is possible.
But it is, at least in principle, it is possible. And these are the type of detailed questions we can answer, or at least address, once we have a measurement of the masses and couplings of these particles.
Great. Well, thank you, Gianfranco. I think
Thank you.
This is very nice. Good night, everyone.